Well, welcome to today's lecture. So today we're going to finish up 10.2. Then we're going to do a little bit of group activity. Today we're going to focus on the formula for the length of a curve. And finally, we're going to revisit the surface area formula. So let's recall what you learned before. Recall that in elementary calculus, you learned that if a curve is given as y equals to f of x, then we can find the length of that curve while x is bounded between two numbers like a and b. We can find the length of the curve when x is in between a and b. So we have a relation between x and y, and x is bounded between a and b, and we can find the length of the curve. So suppose this is your curve C, and A to B on the horizontal axis. Remember that the arc length, or the length of the curve, L, is equal to the integral A to B. You have a definite integral, square root of 1 plus. We take the derivative of y, we square it, and we take the integral with respect to x. Now, we talked about a parametrized curve. Suppose you have a parametrized curve. Let x be equal to f of t, and y equals to g of t. T, the parameterization, or this new variable, is bounded between alpha and beta. Our goal is to find the length of the curve when your x and y are related or dependent on this new parameter or variable t. So this is just pure algebra. What I'm going to do, I'm going to take this quantity inside the radical 1 plus y prime squared, and I'm going to just write it as y prime is dy over dx. So this is 1 plus dy over dx. In the next step, I'm going to divide dy and dx by dt. So here I get 1 plus dy over dt divided by dx over dt. Well, it has exponent 2, so I'm going to raise it to 2. Now, pure algebra. Here we have 1 plus dy over dt squared over dx over dt squared. I'm going to take the common denominator between these two. I end up with dx over dt squared. Here I get dx over dt squared plus dy over dt squared. Well, everything is inside the radical. Now I'm going to take the radical. Square root, square root, square root, square root, and my final square root. Take a look at your denominator. Denominator is a quantity raised to the second power. So I can just take it outside the radical and write it this way. Square root of dx over dt squared plus dy over dt squared divided by dx over dt. And I'm going to flip this guy, and I get square root of dx over dt squared plus dy over dt squared times dt over dx. Note that in this formula, you have dx. dx and dx, they cancel out each other. So L, the length of the curve, is equal to, since it's written in terms of t, we're going to use the boundary for t, alpha to beta, square root of dy over dt squared plus dx over dt squared dt gives dx. And this dx, they cancel out each other. So you get to dt. This is the formula for the length of the curve in parametrized form. This is what you learned in Math 1B. This is your 1C. You're generalizing the idea by defining a parameter, a new variable, and this is the formula like that. Okay, so here let's go over one example to feel more comfortable about this formula. This example says, hey, find the length of a unit circle. Well, okay, a unit circle. First of all, note that a parametrization, a popular parametrization, a common parametrization for a circle, a common parametrization for a circle of radius r is x equals to r cosine theta, y is r sine theta, theta is bounded between 0 to 2 pi. So if somebody says, hey, give me a parametrization for a circle of radius r, this is the parametrization that you write. So now that we have a unit circle, it means that r is equal to 1. So the parametrization is x equals to cosine theta, y is sine theta, and theta is bounded between 0 to 2 pi, one rotation. We have a nice formula to find the length of the curve. L is equal to the integral. My theta or my parameter is bounded between 0 to 2 pi. This is your alpha, this is your beta, so 0 to 2 pi square root of. I need to take the derivative of y with respect to theta, which is cosine theta squared, plus I need to take the derivative of x with respect to theta, which is negative sine theta squared, and find the integral dt, d theta here. So, but inside the radical, you have sine squared plus cosine squared, which is equal to 1. So my L is equal to the integral 0 to 2 pi square root of 1 d theta, or integral 0 to 2 pi 1 d theta. Recall that in Math 1B, we learned that the integral of dx, when x is bounded between a and b, is equal to x. X ranges between a to b, b minus a. So this is going to be just theta, 0 to 2 pi, which is 2 pi minus 0, or 2 pi. This is just the length of a unit circle. Unit circle. 2 pi r, this is the formula. We learned this in algebra, and now this is the actual formula that we use to drive this number. Perfect. So let's move on to the next formula, the surface area. What you learned in Math 1B, and we're generalizing the idea to parameterized curve. So recall that in 1B or in elementary calculus, we learned that surface area for y equals to, for example, f of x, when x is bounded between a to b, is given as s equals to the integral, the definite integral a to b of 2 pi times your function ds. But what was ds? ds was the length of the curve. So you had square root of 1 plus the derivative y squared dx. Well, now we moved on in 1c into a parametrized curve. When you have a parametrization, again, we are here for a parameterized curve. We have the following. We define x to be f of t, x depends on t, y also depends on t, g of t. And t, your parameterization is boundary alpha to beta. So S, the surface area is equal to alpha to beta 2 pi y of t, y depends on t, gt times square root of 1 plus y prime to the second power dx. From the length of the curve, we saw that this is nothing but dy over dt squared plus dx over dt squared dt. This is your formula. The surface area is S equals to integral alpha to beta 2 pi y, whatever your y is, g of t, square root of dy over dt squared plus dx over dt squared dt. Our last formula for 10.2. Okay, this example says, show that the surface area of a sphere is 4 pi r squared. Okay, perfect. So how do you find the surface area for a sphere? Note that since we can use a semicircle, it means that, hey, you have half of the circle. This is your circle with radius r. X can be written as r cosine theta. Y is r sine theta. And theta starts from 0 and starts at pi. So theta is in between 0 to pi. So we can use a semicircle. We can rotate that semicircle and get the sphere. So we have a nice formula. S is equal to, my parameter is bounded between 0 to pi. I have 2 pi y, 2 pi. What is y? Y is r sine theta. R sine theta, this is my y, times square root of dy dt squared plus dx dt squared dt. dy d theta plus dx d theta squared d theta. Well, so the derivative of y with respect to theta is r cosine theta. Then we raise it to the second power. Plus the derivative of x with respect to theta is negative r sine theta. Negative r sine theta squared. Well, simplify this before taking the integral. 0 to pi, 2 pi r sine theta square root of. So here you have square root of r squared. You can factor out your r squared, cosine squared theta plus sine squared theta. And here you have d theta. This is equal to 1. And you get r squared inside the radical. You can just write it out. You get r. So you have the integral 0 to pi, 2 pi r sine theta r d theta, which is equal to the integral 0 to pi, 2 pi r squared sine theta d theta. The whole thing here, 2 pi r squared is just a scalar, so you can write it outside the integral. 2 pi r squared integral 0 to pi sine theta d theta, which is equal to 2 pi r squared negative cosine theta. Theta is in between 0 to pi. You get 4 pi r squared. Surface area of a sphere.